Okay, so let's ask two questions. Question 1. Does this cross-entropy complicated looking error make sense? Does this E in of W make sense? 2. Okay. Well, the prescription was to find the weights W that minimize this E in of W. So how to do that? How to find, weights W that minimize E in of W. Okay, so we'll address both of these questions, and in doing this we will introduce gradient descent, and at the end I'll introduce even another sort of snazzed up version of gradient descent that works very well in practice called stochastic gradient descent. Okay, now does this in-sample error make sense? So let's see. Supposing yn is, so remember we're going to minimize this in-sample error, and ideally we'd like to minimize each term. So let's look at one term where yn is plus 1. So then this is e to the minus of w transpose xn. So we're encouraging w transpose xn to go off. If yn is plus 1, there's a minus here. So e to the minus something large is close to 0, and that's when this term is minimized. Okay. So we're encouraging, so yn equals plus 1 encourages w transpose xn to be much, much greater than 0. Okay. And if w transpose xn is much, much greater than 0, then the sigmoid on that is approximately 1. So for plus 1, this guy is encouraged to produce a probability close to 1. When yn is minus 1, so here now this minus times minus 1 becomes a plus, and so for this term to be minimized, you would like to send w transpose xn very, very small. It encourages w transpose xn to be much, much less than 0, and in that case, when you take the sigmoid of that, you output 0. Okay? So this error function does encourage the same behavior that we saw when we derived the bad error function. Okay, and so there are many ways to develop an error function that has that behavior, that when yn is plus 1, h of xn is close to plus 1, and when yn is minus 1, h of xn is close to 0. Okay, there are many ways to derive an error function that encourages that behavior. The way we chose has the nice probabilistic interpretation of h. It maximizes the likelihood, which is a probabilistic error function, and as we're going to see, when we come to address the second question, it'll be mathematically convenient. Okay, so how to find the weights W that minimize the in-sample error? Let's see how we did it with classification. So classification, what did we do? Okay, it was an iterative algorithm. Pocket algorithm, pocket/PLA. So at every iteration, we try to improve the weights, thereby improving, minimizing E in a little bit at each iteration. At the end, we hopefully have a good set of weights with a very low in-sample error. Okay, or regression. Okay, you could think of the regression algorithm as analytic. So we'll call it the analytic pseudo-inverse algorithm. Okay, which analytically sets the gradient of E in of W to 0. Okay, now in our case we have this complicated in-sample error. So for logistic regression, okay, we could take this approach. This is a nice differentiable error function. Why couldn't we take the approach with classification? Because the in-sample error having h in it, and h being the sign of something, was non-differentiable, was not even continuous. Okay? So this error function is nice and differentiable, and so we could, in theory, set the gradient to 0 and find the weights which achieve that condition. But it's not possible to do it analytically. So cannot analytically set the gradient of E in to 0. Okay. So we're going to use a hybrid of these two techniques. Okay. While we will want to set the gradient of E in equal to 0, similar to regression, we can't do it analytically, so we'll do it iteratively. So iteratively set the gradient of E in equal to 0. Okay, that's our approach. Okay, now I'll give you the high-level philosophy of the approach. And when we were kids, we've all experienced this. So you're on this very hilly landscape. Okay, so you're this very, very hilly landscape. Okay, I don't know what kids play in hilly landscapes like this, but just imagine you're playing around in this hilly landscape with a ball, Okay, so if you randomly throw your ball, okay, depending on where it lands, so the ball could land here, 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 and you'll see why I'm picking these special positions. Okay, so it could land anywhere, so you randomly throw your ball if, let's imagine that it continues like that. And then what happens to this ball? Well, it rolls under the influence of gravity. Okay? And, in these cases, it rolls that way, okay, and comes to a stop here. In these cases, it rolls that way. Oh, what's this ball? It rolls that way and comes to a stop here. In these cases, it rolls that way and comes to a stop here, and so on. Okay, and we're all familiar with this phenomenon. Okay. And, think of this now when you are playing around in real life, this error surface is the height of the hill, okay, the height of the various hills, and, you had an x and a y, dimension that you could move around in. So you have an x and a y dimension. Okay, well, the equivalent of x and y in our scenario are the weights. So you can choose W0, W1, W2, and so on. And for each position in your weight space, okay, there's an in-sample error. So this, slopey, hilly terrain corresponds exactly to E in of W. Okay, and now with the experience you're familiar with, the ball rolls and, let's say, due to friction, comes to rest at the bottom of a hill, at the bottom of a valley. So you can think of these valleys. Okay, these valleys are called local minima. These valleys are called local minima. And we would ideally like to, get our ball into this deepest local minimum. But essentially what goes on is if we threw the ball, it could end up at any one of these local minima, at the bottom of any one of these valleys. Okay? So our idea is to use the surface that is defined by the in-sample error and exactly play this game of throw a ball on this surface and see where it rolls to. When it stops rolling, you've come to the bottom of some valley. Okay? So our idea, so E in of W is the hilly surface. Okay? And so we're going to throw a ball. Okay? Throw a ball and see where it lands, it ends up. Okay. Now, in this general hilly surface, when you throw the ball, it could end up, at any one of these local minima. Okay. And the general task of finding the minimum of an arbitrary function, for example, E in of W, that general task, falls under the realm of optimization, which is a huge area in mathematics. So we're obviously not going to solve the big problems in that area. Okay, so we're going to, just do this simple thing of, following a ball that we throw and see where it goes. Okay, so there are two obvious questions that you might ask yourself when you look at this general approach. Okay, question one. How, when you have, hilly terrains and gravity and so on and so forth, we're all familiar with how the ball rolls and comes to a stop. There's gravity and there's friction. Okay? So how, but in this abstract terrain where the hills are defined by my E in of W, how do we, throw a ball, and how does it roll down? Okay, how do we throw the ball and how does it roll down? Okay, first question. Second question. Okay, we want to find the weights that minimize the in-sample error, but we could get unlucky and end up with weights that have a very high in-sample error. Okay, so how do we get to the global minimum, not the local minimum? Okay, so how do we get to the what's called the global minimum, not the local minimum? Okay, not just an arbitrary bottom of a valley. We want to get to the bottom of the deepest valley. How do we get to the bottom of the deepest valley? Okay. So But how we throw the ball down and how does it roll, okay, it's going to turn out, it's not going to matter too much how we throw the ball, so where you start in this space, and how does it roll, that's what we call gradient descent, so that's what we will derive. Okay? But how do we get to the deepest valley? Well, that's a deep question. So let's answer it. So let's answer this question. How do we get to the deepest valley? Remember when I told you that was the ugly child, but that was the well-behaved child? So we're going to go with the ugly, well-behaved child instead of the nice, easy-looking in-sample error. That's an absolute terror. Okay. Well, we're going to reap the benefits. Because that hilly surface I showed you, well, yes, in general, when you go and try to do in-sample error minimization or minimization of any function, you could have that wiggly surface. And if you had maintained that nice simple error function that we developed first, you would indeed be in that kind of a quagmire. But this in-sample error defines a surface that does not have that wiggliness. Okay, this in-sample error surface looks like this. None of that wiggliness, no local minima, just a global minimum. So all we have to really do is simulate putting a ball somewhere, anywhere, and let it roll. Okay, that's all we have to do. And why is that? It's because it's a nice, well-behaved in-sample error. It's a well-behaved function. So it looks ugly, but it's well-behaved. And that's why we chose it. That's one of the reasons why it's so extremely convenient for us. So we don't have to, we just put the ball and let it roll, and we know that it's going to come to the minimum. Okay. Now, mathematically, this in-sample error is what's called convex, and that's what implies this property. Okay. So what implies that property. And anytime you have a convex error function, you will have this kind of a property, and you don't have to worry about other valleys. There's only one valley, and you'll get there as long as you know how to roll downhill. Okay, so we're now going to develop the methodology that allows us to roll downhill. It's called gradient descent, and it's going to be helpful to have some slides, some pictures to go along with the derivation. So. Okay, gradient descent, or how do you roll downhill? Gradient descent. Now, how to roll downhill. Okay, I mean, you thought you knew how to roll downhill. No, we're going to teach you how to really roll downhill. Okay, now, the picture sort of summarizes what's going on. Okay, and think of the coordinate axes W0, W1, and in general you'll have W2 up to WD. So we're showing 2. Okay, and at any point in this coordinate space, i.e. at any set of weights, you can compute the in-sample error, and that's the height of that surface, that nice colored surface. The colors correspond to height. Okay, and as you vary the coordinate point, as you vary your weight, you trace out this nice, smooth, convex surface with a single global minimum. And now what's the idea? So what's shown there is you're at a point in this coordinate space, you're on the surface, and you look around, okay, and you have lots of directions that are available to you, and you pick one, and you're going to move. Okay, then you're going to look around again, pick one, and move. Look around again and pick one, and move. And that's the basis of this iterative algorithm. Okay, so at iteration t, you're at weights W of t. Okay, and you look around and pick a direction. I'm going to underline direction, v hat. And I'm calling it v hat because it's a direction. So it only has direction. It doesn't have, length. Only the direction is relevant. And so this is a unit vector that corresponds to direction. Okay, so you find a direction and then take a small step in that direction. Take a small step in direction v hat. Okay, so what is a small step? Well, we're going to define a step size. Let's call it eta. So eta is the step size. And let's be cautious, so we're going to pick eta small, so that we look around, figure out a direction to move, take a small step, and a small step, small step, small step. And hopefully in this way, by taking lots of small steps, we ultimately end up at the minimum of the in-sample error. Okay? And so the idea here is that we update to W of t plus 1, from W of t by adding a move of size eta in the direction v hat. Okay. Relatively simple update algorithm. Okay. The problem is, of course, we need to figure out what's v hat. And also, at the end of the day, we have to figure out what the step size is. Okay. But for the moment, it's a cautious, very small step size. So let's go back to what we're trying to do. We're trying to minimize the in-sample error. So we should take a step that decreases the error the most. Biggest bang for the buck. So basically, we're trying to ask, what's the direction in which we can roll downhill, and that's steepest? Okay. So decrease E in the most. That's the idea. Okay. So let's look at what E in is doing. So before the move, you have E in at W of t. And after the move, you have E in of W of t plus 1, okay, which is E in of W of t plus eta v hat, which, okay, because now we have chosen eta small, we can apply the first order Taylor approximation from calculus. This is approximately E in of W of t, the place you started at, plus the move dotted into the gradient, plus the gradient of E in at W of t dotted into eta v hat. Okay, so that's the first order Taylor approximation. If you compare where you were with where you are now, okay, the change in the in-sample error is exactly this term. So the change in E in is approximately eta times the gradient of E in of W of t dotted into v hat. Okay, this is the dot product of two vectors. The Cauchy-Schwarz inequality says this is always larger than the negative of the product of the norms. Okay, so this is always at least minus eta, the norm of the gradient E in of W of t times the norm of v hat. Okay, the minus. So the minus corresponds to the picture. You have the gradient of E in, okay, is some vector, and you're taking the dot product with some other vector. We get to choose this direction, so we should choose this direction to be in the opposite direction, okay, but it must be a unit vector. And then we will accomplish this. We will saturate this inequality. Okay. So the biggest bang for the buck comes from choosing v hat in the negative direction of E in. So v hat should be in the negative direction of the gradient of E in of W of t. Okay. That comes from this analysis where the goal is to minimize, is to decrease the in-sample error of the most. Okay, but this is not generally a unit vector. So to make it a unit vector, we should divide by the norm of the gradient. Okay, and so now we have the direction to move. We have picked a fixed small size, so we move in that direction, and now we reevaluate. Maybe the gradient of the surface has changed, so we pick the new gradient, move, and so on. Okay, so this is illustrated. Okay, so we have a bunch of directions to choose from. We pick one of them, and then we move. So we can iterate this process, move, and so on. Okay. Let's summarize that in an algorithm. Okay. So imagine that you initialize your weights at iteration t equals 0 to W of 0. Now at iteration t, okay, let's suppose you are at W of t. So you compute the gradient E in of W of t, and update W of t plus 1, equal to W of t plus eta times the gradient of E in of W of t. Oh, sorry, minus, because the move is in the negative gradient direction, divided by the norm of the gradient. Okay? And you can update t to t plus 1 and repeat. Okay. And so this implements that idea of finding the steepest direction in which to move a little bit. Find the now new steepest direction, move a little bit, and so on and so forth. Okay. This algorithm is called normalized gradient descent. So we're going to call this normalized gradient descent. Normalized because you take the gradient and normalize it. And you always move in the negative direction of the gradient. And it's interesting. So an interesting piece of information. For any in-sample error, okay, if you take the negative of the gradient, that is a direction in which that error has to decrease. Okay, for some small enough step size. Okay, so we're almost done, except what about the step size? How should we choose the step size? Well, I said you should be cautious and choose a small step size. Okay? But at the end of the day, we've assumed that the step size is fixed. So let me show you what can go wrong. So what is the right step size? Okay, and it's illustrated in the pictures on the right, but I'll draw them over here just as I explained it. Okay, so imagine that here are your weights, okay, and you have a very steep E-in surface, okay, and you're at this point, okay, so you're at this set of weights, and now you take a fixed step size, and that step size happens to be taking you here, so it takes you here. Well, when you make that move, you will find that, the in-sample error suddenly went from where it was to something too big, something much bigger. And then you say, but did you say that the negative of the gradient, so the gradient in this case is in that direction, because that's the downhill direction, so you'll move that way. It's just that, yes, the gradient does give you the direction in which you will decrease the most. Okay, it's the steepest, it's the direction of steepest descent, but it's just that your step size was too big, so that Taylor approximation was not valid anymore. So here the step size, so if this is a step size of size eta is too big. Okay. So you say, well, yes, okay, so in that case we should choose eta so small, so tiny that we'll never run into this problem, or at least when it starts bouncing around like this, so when you get here it'll bounce the other way and then bounce the other way and so on and so forth. So when it starts bouncing around, you're already very close to the minimum, and that eta kind of decides the tolerance with which you will get to the minimum. Okay, so choose a very tiny eta. Yeah, that seems to solve this problem, except, okay, here's what could happen. So it's not quite as steep anymore, but let's say it's something like this. And you're not that close to the minimum, so you're somewhere here. And you knew about this problem, so you chose a very small eta. And then that moved you here, and you chose another very small eta, and another small eta, and another small eta. And you're continuing to make these small moves, move. By this time, you've got married, you've had kids, you've had grandkids. I mean, who cares about minimizing the in-sample error anymore? Okay. So the problem that can arise is if you're very far from the minimum, and you have chosen a very small step size to guard against this, it'll take you forever to get to the bottom. Okay. So ideally what we would like is some kind of Goldilocks step size, okay, where I think about, you're far away. Okay. Ideally we would like to take a big step, okay, and we're still far away, so we take another big step. Okay, and now we've gotten close, so let's take a small step, and then a small step, and so on. But this is not a fixed step size. So here, eta is too small. Here, eta is variable. Okay. So, if we're going to allow for a variable eta, then we somehow need to be able to decide, how far are we from the minimum? Because when we're far away, we want to have a big step size, and when we're close, we want to have a small step size. Okay? We would like this, but we need to know how far we are from the minimum. In general, that's not so easy to do. Okay? But let's try. Variable step size. Variable step size. Okay. Far from minimum, you want eta large. Close to minimum, you want eta small. Okay. Now here's one thing we know from calculus. When you're close to the minimum, and certainly when you're at the minimum, when you're close to the minimum, the gradient of the in-sample error will be approximately 0. When you're far from the minimum, okay, it's not necessarily the case, but usually the gradient is large. Usually the gradient of E-in is much larger than 0, usually. Okay. So this suggests that the norm of the gradient is an indicator of how far you are from the minimum. So, conclusion, choose eta proportional to the size of the gradient. But if eta is proportional to the size of the gradient, and then the direction has the size of the gradient in the denominator, when I multiply these two, the gradient will disappear. Okay? And that leads us to regular gradient descent. Regular gradient descent just says remove the norm of the gradient from in here. Now remember, the norm got in here because we were picking a direction and moving a fixed step. When we remove this gradient, basically what that corresponds to is pick a direction and then move a step whose size is variable proportional to the norm of the gradient. And this algorithm is called regular gradient descent with what's called a learning rate eta. So this guy here is called the learning rate. Okay, and it's summarized in the slide, but you've got the whole idea right here. Now I want to emphasize. Okay. So, star. Okay. So this algorithm, this gradient descent, you can use it to go to the minimum of any convex function, and you can use it to go to the local minimum of any function, providing that the function is differentiable, and you can get a gradient. So gradient descent works for any differentiable E in of W. And our E in of W was a very specific in-sample error. E in of W was equal to, and it's up there, I'll repeat it here, sum from n equals 1 to big N log of 1 plus e to the minus yn W transpose xn. Okay, this is our in-sample error, but you can use it to go to the minimum of any in-sample error. Now, okay, let's look at the cost, the computational cost, because now I want to introduce you to a sort of twist on this algorithm, and the main reason for introducing this twist is efficiency. Okay. So, you can use this to minimize any in-sample error, but it can be inefficient. Okay, and here's the reason. Okay. Let's look at one step. So what happens in one step? In one iteration. Okay. In one iteration, here are the things that you do. You first compute the gradient, and then you update the weights. Okay, now here you have to update d plus 1 weight. So this is an order of d plus 1 operation. But let's look at computing the gradient. Computing the gradient requires you to compute the gradient of this humongous sum. Okay. So you compute the gradient of this humongous sum, which means you have to compute the sum of the gradients of these guys. Okay, which means that you have to compute, and this is an order of d operation, okay, and you have to do it n times. So this is order of n times d. That's costly. If your dimension is 1,000 or 1,000,000 and you have 100,000 data points, that's costly. And you do all this computation for what? For one small move. Okay? So, it's true. Eventually it'll get you to the bottom of this in-sample error, but when? Okay? And so in walks stochastic gradient descent. Okay, so in walks stochastic gradient descent. Which is what I'm going to tell you about next. Stochastic gradient descent, or how to roll downhill efficiently. Now, gradient descent is guaranteeing you that you will always minimize the in-sample error. Stochastic gradient descent does not guarantee you that. The basic idea is very similar to the perceptron learning algorithm, PLA. Okay, so it says, the in-sample error, E in of W, is a sum, is 1 over n, and you can think of this term, so sum from n equals 1 to big N, of a little error for the data point xn. So it's an error between, W, it's an error between W transpose xn and yn. Okay, it's an error that's computed. It's an error term that depends on W, xn, and yn. Okay. And when you compute the gradient, you compute essentially the gradient for all these little error terms. So stochastic gradient descent, or SGD, basically says, don't compute all the individual gradients and then add them up and make one move. Pick a data point. Pick a random data point. Okay, so for this random data point xn, the error that you're currently making is E of W transpose xn, yn. So that's the error that you're currently making. Well, minimize that error a little bit. So in other words, make your move in your weights so that you at least make this data point a little bit better. Okay, so make E of W transpose xn, yn a little better. So what that means is that W of t plus 1 is going to equal W of t minus, your learning rate times the gradient of the little e, not the big E in, E of W transpose xn and yn. Okay? So that's the update. Now, it's kind of crucial that you picked a random data point, because what does that mean? That means that on average, the expected value of this update is exactly this. Is exactly the update. So the expected value of this, expected value, is exactly the gradient of E in. Because you picked a data point randomly. So the expected value is each of the possible values weighted by the probability, which is 1 over n. So you get the sum of 1 over n of these gradients, which is exactly the gradient of E in. Okay, so on average, the gradient that you're using is the gradient that you want to use. Okay, but it's not. But you're picking one term, one data point, and minimizing on it a little. Then you pick another random data point and minimize on it a little, and continue. Okay. So what is this guy? E of W transpose xn and yn is exactly the log of 1 plus e to the minus yn W transpose xn. Okay, so the gradient of this with respect to W, the gradient of E of W transpose xn and yn is exactly minus yn xn divided by 1 plus e to the minus yn W transpose xn. So you can compute this gradient yourself. Okay, it's basically, this is a linear function of W, so you pull down the coefficient, okay, and then you take the log. The derivative of the log becomes, 1 over that. Okay. And then you have to multiply here by e to the minus yn W transpose xn. So the derivative of this guy is this times that, okay, and then 1 times 1 over this guy. So that's the chain rule. But this is exactly equal to minus yn xn over 1 plus e to the yn W transpose xn. Okay, and so we get for this update W t plus 1 equals W of t, okay, minus eta times this guy. But the minus times the minus becomes a plus, so we get plus eta times this guy, which is plus yn xn, okay, times eta over 1 plus e to the yn W transpose xn. So this is the update for stochastic gradient descent. So you pick a random data point, make this update. Pick another random data point, make this update. But here, if I hide that term, you've got W of t plus yn xn. That's exactly the PLA update. Okay. Except the only difference is that you have this weighting term. Okay. And the other difference is in the PLA, xn was a misclassified point. Here, it's a random point. So you will try to improve the situation for any random point. And so, this is the algorithm that people typically use instead of gradient descent just because of efficiency. We would like to use gradient descent, but it's a very costly algorithm. So stochastic gradient descent minimizes the error on, random data points one at a time. Okay. And so it's interesting to just see the performance for that error function that I showed you, the performance of, gradient descent on the left and stochastic gradient descent on the right. And if you look at gradient descent, it very smoothly arrives at the minimum. Stochastic gradient descent is bouncing around. It's bouncing around. It's bouncing around, and eventually makes it down. So it looks like, well, why? Okay, that doesn't look good. Okay, it's bouncing around. So on average, it's making sort of the same progress, but it's bouncing around because, at each step, you're not minimizing the in-sample error, you're minimizing the error on a particular data point, and that's why you bounce around. Usually the price for gradient descent is you have to choose a slightly smaller learning rate. You have to choose a slightly smaller learning rate, but this bouncing around looks less efficient. In fact, it's much more efficient because each of those steps in the stochastic gradient descent is one gradient computation, whereas for the gradient descent, it's n gradient computation. So it's a much slower step, although it looks much nicer. Okay, so that's gradient descent. We've talked about logistic regression. Okay, logistic regression means, predict the probability. Okay, we derive the cross-entropy error function, which is an ugly-looking but very well-behaved error function. It has probability built in, and it's convex. You can optimize with gradient descent. Okay, or if you want to be bold and adventurous and more efficient, stochastic gradient descent. Okay. So, summary of linear models. Classification, we have the perceptron and PLA/pocket. Regression, we have, the W transpose X, the standard linear model, and the pseudo-inverse one-step algorithm that can minimize the in-sample error. And for logistic regression, we have, the sigmoid on the linear signal, and the algorithm for minimizing the in-sample error is gradient descent or stochastic gradient descent. That's a whole new algorithm for you. You can use it to minimize anything you want. Okay. We used it to minimize the in-sample error for logistic regression, getting you to the optimal weights. See you next time.